All right, so imaginary numbers. Do you guys remember what it was? How do we represent an imaginary number? I or j, right?
Oh yeah, didn't like using
So-
J was better.
Can use either I or j. And I think in math they use I, in electrical engineering we use j. But anyways, and they represent square root of -1. Okay, and we did talk about why this, in a traditional way, doesn't have an answer, right? But yet we represent it this way, and then it shows up all over the place. Okay?
Every place.
Yeah. Okay, so then, if I want to say, and then, right, so then I can have, as an imaginary number, remember we said, I can have anything, right? I can have 3j, 1/2 I, right? 2.532 I, or whatever, right? Or it could be negative, could be positive, right? And so then we said these are imaginary numbers, right? Now what are complex numbers?
More imaginary numbers are
So-
being added to
So you have an imaginary part and you have
I guess just a real number.
a real part, exactly, right? So a complex number has a real part, like we present it a lot of times as a plus bj, where a is the real part and b is the imaginary part. Right? Okay? And a lot of times, as a matter of fact, in math, you might say, what is the real part of a plus bj? Well, that is equal to a. What is the imaginary part of a plus bj? That's equal to b. And we write it exactly like this. Real part and imaginary part, right?
How about the vector?
Right, so that was one thing that we didn't cover as much the other day, but I want to go over it because it's very important. So we did talk about the complex plane, right? So again, we have two axes, right? The horizontal axis represents what?
Real.
The real part, exactly. So the vertical axis is the imaginary part, right? And just like in an xy plane, if I give you a number like this, a plus bj, so this axis is basically j, equal to square root of -1, right? So if I come here and say 1 here, that means 1j, right? So therefore, if I want to represent, for example, 2 plus 3j,
Go to 3.
right, I would go to 2 here, the real part,
And
go
then
to 3 here, and so then I look at this point in the complex plane, and so that's going to be 2, 3 on the complex plane, right? And just like in xy plane, have you guys worked with the polar representation of an xy point? Doesn't sound familiar?
No.
That you can say, well, this point I can represent it either by x and y, in this case real and imaginary, or I can represent it by this length r and the angle that this chord makes with the horizontal axis theta.
Whoa.
Because if you think about it, any point in this plane, right, you have to be able to represent them uniquely. Well, if I give x and y, that would be unique, right? Because each point has its own x and its own y. I can do the same thing this way, because any point will have a unique distance to the origin, right? Which we also call amplitude, and a unique angle, right? So, for example, if I have a different point here, the angle might be the same, but the amplitude will be different, right? Or I can have another point here where the length might be the same, but the angle is different. Right? So then by showing the angle and the magnitude, by giving those, I can uniquely represent that point again. Okay? Alright, why do we do that? First of all, to just make life harder for you guys now. So, how do we find, so if I give you the real or an imaginary part, how would I find the length and the angle? So let me just erase this first of all to make it easier again. Right, so I have this length. This is the real part for this point, and this is the imaginary part, right?
And you know it's a right triangle, right?
You know it's a right triangle, exactly. So,
Then you need
if I want to find r, r would be equal to what?
Squared plus b squared. Or in this case, j squared.
So square root of,
Square root of, what do we have? 3?
well, the real part,
Oh,
so-
okay.
real part
Oh.
squared plus imaginary part squared, right? Or in terms of a plus b, the way we have been writing it, square root of a squared plus b squared, right? That would give me r, right? The length of this chord here, right? Which in the case of complex numbers has another name called amplitude. Okay? And a lot of times we also show it as absolute value of a plus bj. That means find the amplitude. Okay? Any questions? So that was the easy part, right? Right? What is, so for this point, as Shiva was trying to do, for that point, what would be the amplitude? The r for that would be square root of
2 plus, or 2 squared
2 squared, so 4 plus,
plus, I guess it's 3j, right? So that's,
so it's only 3, right?
oh, okay.
Just the length.
So it'd be 3 squared, I guess?
3 squared, 9, and I would get square root of 13, whatever that is. Now, if I had done this better, I would have come up with a number that would actually, I can't find the square root of, but you get the idea, right? Okay, now how are we going to find theta?
Oh,
And you know how to do that too, because we've talked about it.
Wait, isn't it like
How are we going to find theta?
but didn't we already like learn?
So what functions do you guys know that
Isn't it-
deal with angles?
Is
sine,
it sine?
cosine.
Sine or cosine?
Yeah.
Exactly, right? So I can write sine of theta as what?
opposite
In
over
this case,
hypotenuse.
opposite over, so in this case, the opposite is what?
The,
3
It's 3 or the, which part?
imaginary.
Imaginary part. So it would be imaginary part over,
real.
Real. Or wait,
Wait, sine is, oh,
over R, right?
r,
oops.
right? Over r, over hypotenuse. Right? Okay. What would be cosine?
Opposite over hypotenuse, so,
Cosine is,
wait. Oh man,
so sine is
Adjacent.
opposite, adjacent, right?
adjacent over hypotenuse.
Which would be
Real.
real
Over r.
over r. Okay. So, one way would be I find r, then I take the ratio and I say this is the sine of the angle, right? So then from there, I actually have to do the inverse sine to find the angle. And don't worry, you don't have to do this by hand. You just plug it into your calculator. And it used to be that we actually, in college, we had tables of the inverse sine, inverse cosine, and we would actually find this ratio, and then we would go and find it in the table, the number that was the closest to it, and then it would say, well, the angle is that. If the sine of that angle is this ratio, it would give you the angle.
That's because you didn't have any calculators, did you?
Yeah, well, we did, but we still, they were giving us those tables, and yeah. But now, you just plug it in, right, and you get the answer.
Or ask Siri.
Or ask Siri, or ask Alexa, or yeah. The thing you gotta be careful about though is, especially on your calculator, you gotta make sure what the setting is, and is it giving you the answer in degrees or in radians, right? And in engineering, we like to work with radians.
Have you guys done inverse sines?
No.
And
Peter, that it says sine, but what it means is the angle whose sine is.
yeah, this the inverse sine to the -1, the inverse, or we used to actually call it arc sine. A sine of whatever.
It just
It's the
means
same
the
thing.
angle whose sine is.
Right.
That's the way you read it. You don't, it says sine, but it really means the angle whose sine is.
Or I could do the inverse cosine of real over the hypotenuse, and then that would again give me the angle. Or what commonly is done. So do you guys remember what was tangent?
Oh yeah.
So tangent, okay, tangent of theta is,
Imaginary over real.
right? So then I don't have to go find r and do this. I can just do, because if I'm given the imaginary and real part, right, I can just now do the inverse tan of that ratio, and then that would give me the angle. Okay, so that's how we would find these things. And then what are we going to do with them? This is a lot of fun for me, guys. Sorry.
So I have a quick question. Do you guys understand why you're doing the inverse? Like the inverse cosine, the inverse tan, and so on?
Not really.
Okay, so if you, yeah, go ahead.
No, go ahead.
Okay, so if you look at both sides of the equation, you have a cosine of the angle. If you take the inverse cosine of that angle, what are you left with?
R real over RT.
Right, so if you don't mind.
Well, okay, yeah.
Right, so you have the cosine of this angle here, right? Yeah, I'll write it out here. You have cosine of theta equals real over r, right? If I do the anti-cosine of the cosine of the angle, it'll also equal the anti-cosine of r of real over that, right? The anti-cosine of the cosine would be what?
Gets rid of it.
Right. So it's just this theta.
He calls it anti, some people call it inverse.
Right.
And
Does that make sense?
Mm-hmm.
In the old days, they called it arc.
All right.
Arc sine.
Because, yeah. That's
Right.
my.
Because if I give you the angle and you take the cosine of it, that is equal to that ratio, right? But we're trying to go the other way around now, right? To find what the angle would be if I have the ratio. What angle would give me that ratio, right? That's why you have to take the inverse, go the other way. Okay, cool. So once you have this and this, you know, so we started with A plus BJ, right? If I have R and theta, now I can write A. Actually, let's write down what A is. So cosine of theta was what? If this is A and this is B, right? Real and imaginary. Cosine of theta was what?
Real over R.
So in this case, real is A
Yeah,
over
A
R,
over.
right? So therefore, A can be written as R cosine of theta, right? Okay, what was sine of theta?
Imaginary over real, or R.
So b over r. So then I can write b as r sine of theta, right? So then I can plug these in here and write my complex number as r cosine theta plus j r sine theta. Okay, now here comes the fun part. You thought this was confusing.
Well, this is the magic of mathematics, you know, it brings things that, holy mackerel, is that true? But you just proved it, yeah, it's true.
This is equal to r e to the j theta. And this notation is the one that we use a lot in electrical engineering.
And how you got to that, some super mathematician figured that out.
So I can give you how you can get to this, right? By writing cosine and sine in terms of e to the j theta. But why sine and cosine can be written in terms of e to the j theta, that is, yeah, that gets a little bit more involved.
Hey, that's mind-boggling, this E, where does E come from? You know, it's this magic number that pops up all over the place, and this crazy number to an imaginary power, I mean, that's gotta blow your mind. And you don't have to, you know, you can relax. You don't have to intellectually understand it. That worried me. I said, I'm missing something. I should be understanding that. I'm gonna flunk. I don't. Guess what? You cannot understand e to the j theta, where that comes from. You know, you just have to use it.
Yeah, so what Dr. Winter said is very true. For a lot of, you know, I've run into a lot of people in electrical engineering, the ones that are truly thinking as an engineer, right? We want to understand where this comes from. If I don't understand it, yeah, I feel like I'm missing something. It took me a couple of years, really, to get a feel for it. To kind of, okay, all right, I think I feel comfortable with it, that I can manipulate it. I might still not understand exactly where it's coming from, but I feel comfortable enough that I can work with it. And the thing is, as I said, this is going to be all over the place. Okay, so it's important to understand this. And that's why we're talking about it here. Okay. Any questions? So the thing, at the end of the day, the things that you guys need to know is that I can go from complex number, I can write a complex number in terms of the amplitude and its angle on the complex plane in this format. So you need to know this format. This is useful, you need to know this, but you can derive this, right? If I put it on a complex plane, I can look at the angle and figure out, oh yeah, my real part is r cosine theta, my imaginary part is r sine theta. So you need to be able to write it in this form. And then you also need to know that the amplitude of the complex number, which is equal to square root of a squared plus b squared, is equal to r. And then theta, or yeah, I guess to be complete, they also show this as the angle of the complex number a plus b j is equal to theta, and this is equal to tan. Let me follow the same, so is equal to inverse tangent of theta. Sorry. B over A is equal to theta. Those are the things you guys need to know. And the worksheet I'm going to give you, you're going to need these things to work through them.
You know what E is? What's E? What's the number? What's the value?
10, right?
E?
Or, oh no, E's 2, or 2, I don't remember the
It's
rest.
the 2 point, I never remember,
7.3
7
Yeah.
3 something.
And where did it come from? Nobody knows. I mean, E,
Came from
E-
Euler,
Yeah, E stands for Euler. He was this guy,
Mr.
super smart guy,
Yeah.
and he figured out that number E, and you don't want to know where it came from.
Wait, but why, like,
It happens in nature.
Hey, that's one of
All
those
over the
questions,
place.
Peter. That's a really good question. Why? You know, why? What about pi? Why?
I mean, pi is a really simple example because it's the ratio, right, of the circumference of a circle to its
Yeah.
diameter.
Yeah.
And it happens in nature. And it turns out to be this irrational number that goes on forever. That still boggles my mind whenever I think about it. It's like, why? I mean, I think God really wanted to play a trick on us. Let me give them this really... Now, my other theory is that in some other dimension, it actually turns out to be an exact number. We just don't know what that dimension is.
Interesting. And E is probably some great thing,
And
you know.
E is
The
probably...
ratio between the sun and the moon, or the Venus and Mars, or something.
So, do you remember you guys were talking about if you lived in a plane and somebody came and poked a hole in the plane?
Oh yeah.
It seems like, hey, there's this thing is opening up and closing, and I have no idea where it's coming from, so this might be one of those things. We don't know why, but... Anyways,
So
okay.
this is really fun. We're playing with imaginary numbers that don't exist. We're playing with dimensions that don't exist.
But we make real good use of them.
Well, that's this cool thing. All this stuff is going to end up with how you design a motor, or design an atomic bomb, or something.
Motor to atomic bomb. Big jump there. All right.
will we do that someday?
Uh,
Our last test?
the final project, and I mean final. All right. Any questions? Okay. So if you guys recall, we also talked about additions and subtractions, and basically mathematical operations with complex numbers. Okay. So let's review that really quickly.
Are you going to show them how you can use this with figuring out your course, that airplane's course over the ground in a windy, when it's flying in wind?
So yes, that's when. Yeah, I gotta see how I'm gonna get to there. So first summation, easy, right? You guys tell me. So if I have a plus bj, that's one complex number, right? Plus c plus dj, what do I get?
E plus...
So the trick with complex numbers is that we always want to write it in terms of its real part and its imaginary part, right? So the question is, what is the real part of the result?
A plus C.
A plus C, okay,
And then the BJ, so plus.
plus
B.
B plus D J.
Ah,
Easy,
Yeah.
right? So this is my real part again, this is my imaginary part.
Wait, I have a question.
Mm-hmm.
So B and D would be real numbers, though, right?
A and B are always real numbers.
B and D are real numbers too.
Yeah,
Oh,
Good question, Peter.
and I guess the other thing I forgot to mention that a lot of times you might say I have a complex number C1 plus a complex number C2. We might just say that. But we know that that C has a real part and an imaginary part. And that other one, right, each one of them has a real part and an imaginary part. And sometimes it might happen that either the real part or imaginary part might be zero, right? I might have a complex number that's 0, for example, plus 3j. Well, that turns out to be just the imaginary number 3j. Or I might have another number that is 2 plus 0j. Well, that's just the real number 2. So real numbers and imaginary numbers are, what do we call them? Forget the term. The complex numbers are the more general, right, set of numbers. And the real and imaginary numbers are the ones that either the real part is 0 or the imaginary part is 0. All right, so, and I think this is what Dr. Winters was kind of mentioning earlier, that if I show these two numbers on the complex plane, if this is A, B, and this is C, D, right? Again, this is the real, and this is the j-axis, right? And I can show now this number as this, and this complex number as that, right? So I have R1, R2, and then I have theta 1 and theta 2. What does that mean when I add them?
You're getting the whole. Wow.
Would you get like the points and then?
You're just.
So the cool thing is pictorially. So first of all, I'm saying A plus C, right? So if I look at it over here,
Yeah.
right? This is A and this is C. I'm getting A plus C. So it's going to be somewhere over here. A plus C. Oh, C.
You're just expanding it both ways.
Right? Yeah. And the other way. And hey guys, remember that these could also be negative numbers.
Oh yeah.
For simplicity, we always show them in the first quadrant, but they could be negative numbers. But the cool thing is pictorially, if you did this, right? If I did A plus C here, and then up here, if I did the B plus D, it's the same as drawing, if I call this a vector, drawing the same one from this point, and drawing another, like this one up here, the sum is this.
And that's the point.
That would be the point.
Oh wow.
Yeah, yeah. Whoa. That's right.
Oh, but the way I love to see it is, I was a pilot in the Navy, okay, and flew a lot of times, and when you're flying over the ground like this, and there's a wind, what's your path over the ground?
So guys, look, let's say this is the plane that Dr. Winters was flying. Oh wait, you need another wing down there, sorry. Right? And he's flying this way. Well, let's say this is the actual runway.
Mhm.
There's a wind blowing this way, right? And he wants to land this way. He actually has to have the nose of the plane going that way, so that the sum of the two, the wind and the plane, the velocity of the plane, would make it come this way. So if you watch the footage of some planes landing in really windy days, you actually see the planes coming down like this.
Yeah.
They're coming in an angle. All right, guys, so A plus BJ minus C plus DJ. How would I write that? Shiva, give me the real part.
That'd be A minus C,
A minus C.
and then plus, it would be B minus D,
Exactly. B minus D
and then, yeah.
J. Right? Easy, right? Now, A plus BJ times C plus DJ. So now we're doing multiplication of complex numbers. Okay,
It would be.
Peter,
So it'd be AC,
AC,
and that's the real part, or
Uh-huh.
yeah, the real part,
uh-huh,
and then it'd be. Would it be plus or time? No, it'd be plus B, BJ. Wait.
okay, you know what?
Okay.
Let's do the imaginary part first.
Isn't J squared
That's
just
easier.
1?
Aha. Aha. So if J is equal to square root of -1, what is j squared?
1.
Negative 1.
Negative,
Oh, negative 1, yeah.
right? Because that is this, which is that, right? So then, where Shiva is going is if I have bj times dj, what would I get?
B minus, or B plus.
No, bj times dj.
Oh.
Negative B, D.
Do you see that, Peter?
Okay, what
Right?
is it?
So I would have plus bj times dj,
Which is BP
bd
times negative 1.
times negative 1, right? So then I can write this, therefore, as minus bd. There's no more j, right? J squared, negative 1. J is gone. I don't have j anymore.
I like that.
But not completely. So what happens to the imaginary part now? So Peter,
No.
give me the imaginary part.
Would it be A, DJ? Because,
A, right, A, D, J,
plus, C, BJ.
excellent. Or we'll just take out the J
Oh, yeah.
and put it here. So now this is the real part, and this is the imaginary part. Right? Now here, if I wrote this as R1 e to the j theta 1 times R2 e to the j theta 2, what would that be?
Well, they're different power variables, right?
So,
So you can't simplify it.
well, let's say I have ax to the n times bx to the m. What is that?
Oh, it would just be AB
AB.
X
and
M
plus, yeah.
Plus M.
Okay, so what is that then?
Oh, because E's the same, so it'd be R1, R2,
R1, R2,
E, and then J theta 1 plus J, or you could just do J squared.
excellent. So when we do multiplication, using this format actually makes it much easier, right? Until we get to the point that I need to find out what the real part is, then I still have to go back, right? But actually the good news is that a lot of times we work with the amplitude and angle. Okay? Alright, so last one left. Who wants to attempt this? A plus bj over c plus bj. So now we're dividing two complex numbers, right? This is c1 divided by c2. c1 divided by c2. Complex? Yeah. I gotta double check on that bar.
Well, back in the old days.
I think you're right. I just gotta, yeah. Okay, so we're doing this. So, let's do it the easy way first. Again, if I write this as R1 e to the j theta 1 divided by R2 e to the j theta 2,
You get R1 over R2, and then you can simplify the E.
which
But
would be,
J theta 1 minus, well, you could simplify the J's. Yeah.
exactly, right? So again, if I have it in this form, I can easily now say this is the magnitude of the resulting value and this is the angle of the resulting value, right? If I really want to work with this, you guys remember the trick to do this?
Separating the real, well, I don't know.
So we always want to write it in terms of the real part and imaginary part on top, right? We don't like
Yeah.
having it on the bottom. But how do we get rid of it on the bottom?
C to the negative 1 power. And
Well, no, but I still have to keep the same value, right?
Oh.
Yeah, I can write it as that, but so if I multiply this by c minus dj over c minus dj, this is 1. right? So I can do that. I still get the same value, right? But when I do this multiplication, we talked about it last time, you guys can go and verify that's the case if you want to. You get c squared minus d squared. So I don't have any more j's. And remember, if you remember, by the way, this has a special name. Whenever I take a complex number and write it with the imaginary part as a minus, this is called the
Isn't
the complex, yes. No, what
C
the
squared-
conjugate, yes.
Isn't that c squared plus d squared? Am I wrong?
You're correct. It's plus because of the j. Yes. C squared plus d squared.
Oh, yeah, because it's -1 and then it cancels out.
Yes. You get c squared plus d squared. This is called the conjugate of the complex number, right? And then you work out the top, just like when you're doing the multiplication, right? You get AC plus BD, and then here I get plus, and I have BC
Oh.
minus, I'm just kind of trying to put the minus over here, but
Oh,
yeah, you're
okay.
right. So it would be AD J. So this is the real part, this is the imaginary part.
The life of me, I cannot imagine when I want to divide complex numbers. I can't even imagine when we want to multiply them. But there's probably a reason. There's probably a place.
And yeah. When we put, for example, a capacitor in series with a resistor, you're going to get a division of complex numbers. And that's when you want to simplify it like that. So as I mentioned, right, with our audio amplifier, remember we're biasing our microphone, right? We had a 2.2K here, VCC, and then we came out here and we went to a capacitor, right? And then I go to some other stage, right, where my amplification is happening, right? But for now, let me just say that we represent the next stage as another resistor, okay? And we call this our load. Now, what did this do?
Oh, it took away like the DC.
It took away the DC bias,
Yeah.
right? Because we have a DC bias here. I want to get rid of the DC bias. I put this here. But if you're not careful about the value that you pick here, in conjunction with what this resistance is, you could actually get rid of your audio signal as well. This turns out, when we look at the combination of these two together, right, when you put in a sine wave through, if you put in a sine wave through, the response of this circuit is frequency dependent. It's a function of frequency. So for certain frequencies, including DC has what frequency? That was a tricky one I gave you last week, remember? When you were plotting your DC biased sine wave in frequency domain, the DC had a frequency of,
Say it, Peter.
okay.
It's on the tip of your tongue, you're right, say it.
Remember, like I said, you have your V of t was equal to like 5 plus 3 sine, I don't know, 200 pi t, right? What is the frequency of this part?
Is it around 100?
Yes,
Very good.
100 hertz. Right? What is the frequency of this part?
5. Or no, sorry.
Okay, what's the amplitude of this part?
3.
3. Amplitude is 3. this part,
That's. Oh wait, I remember this. It's always.
That's reactive, right?
Wait, isn't it?
this is a DC part. Right?
Oh.
And then, but isn't it one where we're like plotting the frequency, and then it was just like going up or something?
Yeah, so when we plotted this one we said here's 100, right? This was amplitude 3. For the DC portion, we were here.
What would it? Oh.
And it was like 5.
Yeah.
So the frequency was 0. If you think about it, DC is not going up and down. It's staying constant, right? So there's no frequency. Frequency 0. Right? So anyways,
And the period is forever.
so if I'm putting a sine wave through here, the response of this is frequency dependent. That is why it actually kills DC. And if we look at, again, we look at this eventually, it's going to look like this. The response of it. Which means it's going to kill a lot of the lower frequencies, and then it's going to come, and at some point, the higher frequencies are going to get through as is. And if you're not careful, and you push this too far, you're going to kill out all of the audio components, the frequencies of the audio component. That's where these things come in. And to analyze this, to figure out the impedance of this whole thing, for C, for a capacitor, the impedance of it, which we write as Z, is equal to 1 over SC,
Yeah, we haven't talked about S.
right, where S is a complex number, delta plus J omega. Where omega represents the frequency, remember that omega in here? We had omega. That represents frequency. This represents the DC part of it, okay? And then I'll talk about how we then simplify all of this. That's where we're going.
Whoa.
So to be able to do this, you need to know that.
And impedance is like resistance, okay? The impedance,
Isn't it like total resistance or something like that?
it's a combination of complex and real. But the impedance of 1 ohm resistor is 1 ohm.
Yeah, so impedance of a resistor is real. It doesn't have an imaginary part. But the capacitor and inductor, they do have imaginary parts. And you go, well, wait a second. I thought imaginary things are not real. How could a capacitor and an inductor have non-real
You know,
things?
A good,
These are mathematical, what do we call them? Constructions, the mathematical tools that we use to describe how they behave.
but it's true, if you took a big capacitor, plugged it into the wall there, ideal capacitor, you generate all sorts of current. But would the electric company charge you any money for it? No, because all the current was coming in and then you're pushing it back. It comes in and goes back. So it's sort of an imaginary current because it doesn't make any heat, it doesn't do anything. You give it, take it away, give it.
So, again, don't worry, like, you have to let these things sit for a while and kind of simmer, right? And then eventually you kind of get a feel for it, and then it kind of starts making sense. Okay, I think it's just like the example that Dr. Winters just used is one way of looking at it, right? And it will come after some time.